Hello everyone and welcome to Seminar 8 of your course. This is the final seminar for this course, so I do hope that these sessions have been helpful. Let us take a look at the topics that we are covering in this seminar. The topics covered in today's seminar are related to the frequency response of systems, that is, the response of a system to a sinusoidal input of certain amplitude and frequency. To analyze this frequency response of systems, we use the frequency transfer function and the concepts of amplitude ratio and phase angle, which are the magnitude and phase of the frequency response transfer function respectively. We will also take a look at the Bode stability criterion and the roles of gain margin and phase margin in assessing the stability of the system. All of these topics are, of course, already being taught to you by Dr. Lee and are available in your e-class lecture notes or will be uploaded soon. So let us move on straight to the questions. In question 1, we are given a process described by the transfer function Gp of s equals 1.5 over 10s plus 1, a valve whose transfer function is given by Gv of s equals minus 10 over s plus 1, a sensor whose transfer function is given by Gm of s equals exponential of minus 0.5 s. The given controller settings are a controller gain of minus 0.72 with integral time of 3.74. Part A of question 1 asks us to calculate the frequency response of the open loop transfer function GOL and to use the Bode stability criterion to analyze the stability of the feedback control system. The open loop transfer function is given by GOL and is the product of the controller, valve, process, and sensor transfer functions. The frequency response transfer function is obtained by substituting S equals J omega in the open loop transfer function. Let us have a quick recap of the frequency response and Bode stability criteria concepts. For a system G of S, the frequency response is the response of a system to a sinusoidal input A sine omega t, and it is denoted as G of j omega. This G of j omega can be rearranged into one of two useful forms, the Cartesian form and the polar form. The Cartesian form is given as G of j omega equals real part plus imaginary part, both of which are functions of omega. The amplitude ratio for this form is given by AR equals the square root of the real part squared plus the imaginary part squared. The phase angle is given by phi equals tan inverse of the imaginary part over the real part. The polar form is given in the form of numerator polynomial over the denominator polynomial, where both polynomials contain real and imaginary parts as well as exponential terms. The amplitude ratio and phase angle are given by the following formulae. The frequency response of n number of systems in series is given as follows. The overall amplitude ratio is the product of amplitude ratios of all n systems, and the overall phase angle is the sum of phase angles of all n systems. The Bode diagram comprises two log-log plots. The upper plot is the scaled amplitude ratio versus omega tau, and the lower plot is that of the phase angle versus omega tau. Let us go through a quick overview of how to plot a Bode diagram for a system G of S. We start by finding the frequency response of the system. We use the frequency response to find the amplitude ratio and phase angle. We scale the amplitude ratio and use it to plot the upper plot of the Bode diagram. We then find the low and high frequency asymptotes for both AR and phi plots by considering omega tau tends to 0 for the low frequency asymptote and omega tau tends to infinity for the high frequency asymptote. We find the frequency at which these asymptotes intersect by setting omega tau equals 1. The Bode stability criteria states that a system G of S with frequency response transfer function G of j omega is unstable when its magnitude equals 1 and its phase equals minus 180 degrees. The frequency at which the magnitude of G of j omega equals 1 is called the gain crossover frequency, and the frequency at which the phase of g omega equals minus 180 degrees is called the phase crossover frequency. Here, regard the term crossover to mean to cross over into the unstable region. The quantities gain margin and phase margin measure how far the system is from the crossover region. So let us get back into question 1, part A. So far, we have found the open loop transfer function and its frequency response transfer function. From this g of j omega, we can find the amplitude ratio and the phase angle for the open loop system. To check if the system is open loop stable, we can set the open loop phase angle to minus 180 degrees and solve for the phase crossover frequency, which is calculated to be 1.15 degrees. At this crossover frequency, if the open loop amplitude ratio is equal to 1, then the system is unstable. However, at this phase crossover frequency, we find that the amplitude ratio is 0.63, which is lesser than 1, and therefore the system is stable. Part B of question 1, we are asked to find the amplitude of the output signal given an input sinusoidal set point change given by 1.5 times sine 0.5t under open loop conditions. From the frequency response of the open loop transfer function given here, we have the amplitude ratio given by the following expression. For the given sinusoidal input change with frequency omega equals 0.5, we have open loop amplitude ratio at omega equals 0.5 equals 2.14. Amplitude ratio is the ratio of amplitudes of output to input signals, and therefore the amplitude of the output signal is given by the amplitude of the input signal times the amplitude ratio of the open loop at the input signal frequency and is calculated to be 3.21. In part C of question 1, we are asked to find the amplitude of the output signal when the same sinusoidal set point input signal is applied, but under closed loop conditions this time. The closed loop transfer function is given by the product of all the transfer functions in the forward path over 1 plus all of the transfer functions in the feedback loop and is given as shown. The amplitude ratio is computed for the frequency response transfer function of the closed loop. We can make use of the open loop amplitude ratio at the given input signal frequency to compute components of the closed loop amplitude ratio. The phase angle of the closed loop is calculated to be minus 2.578. Using the open loop amplitude ratio, it is easier to rearrange the closed loop amplitude ratio expression to take the polar form instead of the Cartesian form here. Using Euler's formula for exponential of negative j theta further simplifies the polar form of the closed loop amplitude ratio, which is calculated to be 1.528. Then, the amplitude of the output signal for the given input sinusoidal set point change under closed loop conditions is calculated to be 2.29. Let us now move on to question 2. In this question, we are given a heat transfer process described by the transfer function between output and input, that is heat and flow, given by 3 times 1 minus s over s times 2s plus 1. We are told that the input signal varies sinusoidally with amplitude 2 and period 0.5. We are asked to find out what the amplitude of the output signal would be for this input when the transient behavior dies down. Let us rearrange the information we have about the sinusoidal input into its general A sine omega t form. We then get the input signal to be 2 sine 4 pi t. The frequency response transfer function for this process is given as follows. The amplitude ratio for this frequency response transfer function is given as 3 times square root of 1 plus omega square over omega times square root of 1 plus 4 omega square. From the definition of amplitude ratio, the amplitude of the output signal is equal to the amplitude ratio at the frequency of the input signal, in this case at 4 pi, times the amplitude of the input sinusoidal signal itself, which in this case equals 2. Therefore, the amplitude of the output signal is 0.24 liters per minute. Let us move on to question 3 now. In this question, we are given the overall transfer function of the process, valve, and transmitter in g of s equals 2 times exponential of minus 0.2 s over s plus 1. Note that the units of the time constant and the time delay terms in this transfer function are in minutes. Our task is to design a proportional integral controller and to compute the gain margin using two methods. The direct synthesis method, where the desired closed loop time constant is 0.3 minutes, and the phase margin method, with phase margin equals 40 degrees, where the integral time is 0.5 minutes. Let us tackle part A of the question, which asks for a PI controller to be designed using the direct synthesis method. From the formula of the direct synthesis method, we have the controller gain, Kc, equals 1 over k times tau over theta plus tau c, and tau I equals tau. We are told to take the closed loop time constant to be 0.3 minutes. Therefore, we compute Kc to be 1 and the integral time to be 1 minute. To find the gain margin, we first need to find the phase crossover frequency, that is, the frequency at which the phase angle of the transfer function is minus 180 degrees. Therefore, equating the phase angle expression to minus 180 degrees, we get the phase crossover frequency to be 7.85 radian per minute. Having computed the phase crossover frequency, we can compute the gain margin as the reciprocal of the gain at the phase crossover frequency. This gain is calculated to be 0.255, and therefore the gain margin is taken as the reciprocal of AC, which is 3.93. In part B of the question, we are asked to design a PI controller with integral time 0.5 minutes using the phase margin method, where the phase margin given is 40 degrees. The phase angle at the gain crossover frequency is calculated as the phase margin minus 180 degrees, which gives us minus 140 degrees. Equating the phase angle expression at gain crossover frequency to minus 140 degrees gives omega gc equals 3.04 radians per minute. We also know that at gain crossover frequency, amplitude ratio equals 1, and therefore Kc is computed to be 1.34. Then, solving for phase crossover frequency by equating phase angle at omega Pc to minus 180 degrees, we get the phase crossover frequency to be 7.19 radians per minute. Then, the closed loop gain is computed to be 0.383, and the gain margin is calculated as the reciprocal of the closed loop gain, which equals 2.61. In question 4, we are given the transfer functions for the controller, valve, process, disturbance, and sensor. Our task is to find out the value of controller gain that provides a phase margin of 30 degrees and to calculate the gain margin when Kc equals 10. From the open loop transfer function given by the product of Gc, Gv, Gp, Gd, and Gn, we have the open loop frequency response transfer function as shown. The amplitude ratio and the phase angle are calculated as follows. Given the phase margin of 30 degrees, the phase angle at gain crossover frequency is calculated as minus 150 degrees. This gives us a gain crossover frequency of 1.72 radians per minute. And upon substituting this gain crossover frequency into the ratio AROL over Kc, we get a value of 0.144. However, since we know that at gain crossover frequency, the amplitude ratio of open loop equals 1, we get a value of Kc equals 6.94. In part B of the question, we are asked to compute gain margin given Kc equals 10. For this, we first compute the phase crossover frequency to be 4.05 radians per minute. Substituting the value of omega Pc into AROL over Kc, we get 0.0326. And upon using the value of Kc given to us, that is Kc equals 10, we have the closed loop gain equals 0.326. Therefore, the gain margin is computed as the reciprocal of closed loop gain and equals 3.07. So this brings us to the end of Seminar 8 and the sessions for this term. Thank you very much for your patience and attention, especially as we switched modes of instruction. Please feel free to contact the TAs with any doubts or queries and any feedback as well. Stay safe and take care, everyone.